now we're on to changes of state and Le Chatelier's principle. So if you hear somebody come through at some point and talk, that'll be my brother Andy. He's a graduate of Notre Dame, just got his MBA up there, unemployed. So he's actively looking for a job. So if you'd like to offer him one, or your parents would like to, please get in touch with me. All right, let's get to the podcast itself. Changes of state. Make sure you guys get this stuff in your notes. Highly important stuff. Why, yes, I do have a diagram that you can look at. Let's look at a diagram, and we'll look at what happens during a change in state. This is a diagram showing what happens when you take and add calories or heat to a system. So this could be a container of water. You're adding heat on the bottom, and then your y-axis over on the side is temperature, okay? So we can fill in the temperatures. And if you guys will, just go ahead and sketch this out in your notes real quick. Hit pause and go ahead and sketch this out in your notes. And when you come back, we'll talk you through what the different parts are. All right, first of all, let's fill in a couple landmarks here. You can see over here on the left, I'm making a couple marks, all right? So this is 100 degrees. You can say, hey, Andy. Andy, my brother just walked in.
Hey, everybody. Danny's lying. It's not 100 degrees outside yet.
It's 0 degrees down here at the bottom, 100 degrees at the top, okay? Because we're talking about water right here. So water freezes at 0 and boils at 100, all right? So let's call this one down here, this temperature, -10. And this one 110. Up there. All right. So now that we have 0 and 100, that kind of sets the stage for where we are. Let's talk about what's happening during each one of these legs, leg A, B, C, D, E. So the molecules down here at the very, very bottoms, at -10 degrees, are frozen. This is ice, right? So go ahead and you can go ahead and label that this is ice and be a very happy person. The ones here in the middle, leg C, those are liquid water, so we'll write water. And the ones up here in leg E, those are all steam. Okay, the 3 phases of water. And here in the first leg, leg A, you'll notice that what's happening is as you add heat, the line goes up. So as you add heat, the temperature increases. So we're going to say that in leg A, in leg C, and in leg E, the heat makes molecules speed up. Because remember, part of the KMT was that the temperature is directly related to the speed of the molecules. So heat makes molecules faster. That's a horrible faster, sorry. All right, so the energy is being used to give the particles more kinetic energy and thus more motion, and we register that by measuring the temperature, okay? So those 3 are pretty easy. You've always learned that when you add heat to something, it gets hotter. That just makes sense. What we have to talk about is what happens in leg B and leg D. So in these 2 legs, the temperature is constant, okay? So make sure you realize that this is a constant temperature. So now that we know that in B and D, the temperature is not changing. Well, why is that? What's happening? Well, in this leg D up here, the water is changing from water to steam. It is undergoing a phase change. And during a phase change, temperature does not change, right? That's something you guys definitely need to know. During a phase change, temperature doesn't change. Leg B right here, this is ice melting, right? So this is ice changing into water. But again, the temperature doesn't change. So what really is going on? Well, the energy that you're adding in both leg B and in leg D is not being used to speed up the molecules. That energy is being used to break bonds. Okay, so if you're adding energy to it, you're not using that energy to hit the molecules and thus give them more energy to speed up. You're using that energy to break bonds. And notice the temperature doesn't change until all of the ice is melted and it's all water. The temperature up here doesn't change until all the water turns to steam. Okay, we would say, well, where does the water start to boil? Okay, that's right here, right? Where is the water where is the phase transition half water, half steam? When is half of it boiled away? And that would be right here, halfway along that line, okay? Where is it pretty much all ice and just a little bit of water? That would be really close to this end, because at that point, very little of the ice is actually melted, okay? So in the parts that have a slope, we will say that the energy is being used to speed up molecules, not to make them hotter. Don't say that. It's being used to speed them up. And down here, the energy is being used to break bonds. Now, what happens if you went backwards? What happened if you started at hot temperatures and took heat away? Well, what would happen is energy would be released because you're sucking away energy, so energy has to be taken from something. Energy would be given up as the steam turns into water. Energy would be given up as the water turns into ice. Okay, energy would be given up as the molecules slow down. All right, so this works both forward and backwards. But that's a phase change. Why, thank you. I thought that was awesome myself. All right, let's summarize. This is true. In order to change a liquid to a gas, you have to absorb heat from the surroundings, and that's also true to change a solid to a liquid. You have to absorb energy. That makes sense. If you think about it, it takes heat or energy to melt ice, right? But if you go backwards, if you go from gas to liquid or from water to ice, it gives off heat. This is something you may not think is true. When water freezes, it actually gives off energy. Well, that sounds weird to you, but it's not that it gives off energy to itself, it gives off energy to the surroundings. So a lot of the times in Madison, Alabama, when it snows, it starts to snow and then it turns to rain. And why is that? Because the snow crystals, as they form up the atmosphere and start to freeze, they will actually warm the atmosphere because they're giving off energy to the atmosphere. It starts out as snow and then it turns to rain quickly thereafter. So it's not often that we get just tons and tons of snow. So there's this dude named Le Chatelier's principle, and Le Chatelier actually has this funky hat over the A in his name. So you can put this little circumflex, if you don't know what that is, look it up, over his name, because that's how you're supposed to put it. And his principle states this. Here is a beaker full of ice at equilibrium, meaning you have some ice and some water. It's just sitting there. And if no energy comes in and if no energy comes out, that thing will just stay ice and water. Okay, same amount of ice, same amount of water, forever and ever and ever. So if you stress it in some way, change it in some way, it must adapt to that change, right? So let's say you added heat to this beaker of water and ice, some of the ice would melt. So you get less ice and more water. If you took away heat from this system, absorb the heat somehow, it would change some of the water into ice. That's all Le Chatelier's principle says. All right, you need to know the difference between volatile and non-volatile liquids. And these is more of just definition thing, right? So think of something that's volatile: gasoline, alcohol, fingernail polish remover, ladies, acetone, ethyl acetate. Those are all things that are volatile, meaning they evaporate easily. Rock, that would be non-volatile. Even as a liquid, it doesn't really evaporate very well. The heat of fusion is the heat necessary to melt ice. It's usually measured in kilojoules per mole. Heat of vaporization is the heat necessary to boil water, measured in kilojoules per mole. Now, since we've been talking about changes of state, we want to talk about what happens when you change the pressure on a system. Because when you change the pressure, that's a Le Chatelier's principle thing. So a boiling point is when the vapor pressure being given off by the liquid is equal to the atmospheric pressure. So what creates vapor pressure? Well, water molecules turn to a gas. They evaporate, right? And those water molecules, now that they're water vapor molecules, run into things. They hit things, and they create vapor pressure. The more water molecules you have, the more vapor pressure there is. Or the warmer those water molecules are, the more vapor pressure they are, because they're going faster. So those things create vapor pressure. So if you have high atmospheric pressure surrounding the thing, it won't boil, because you've got to reach enough vapor pressure to overcome the atmospheric pressure. If you have hardly any atmospheric pressure, it's not very hard to boil something at all, because now it boils at a much lower temperature. Okay? If pressure goes up, the boiling point goes up. If the pressure goes down, the boiling point goes down. This is a phase diagram, and a phase diagram just tells you for a given pressure and a given temperature, what is the phase of matter. So you could pick a given temperature and pressure and go, oh, that's in a liquid state or a solid state or whatever. You guys are going to need to know how to read one of these, not to draw one of them necessarily, but just how to read one of them. We say that down here, see where it says 1 right there? That is the normal pressure. Where it says 1 atmosphere, that would be the normal pressure. So that would be the phase change when you're just at normal air pressure around you. This point right here in the middle is called the triple point. This is the point at which you can get all 3 states of matter occurring at the same time. And this is called the critical point, where it doesn't matter how much pressure you apply, that can't stay into a liquid form anymore. It has to form a gas. At this point right here, you get this thing that even though you've applied a great deal of pressure, it's going to want to turn into a gas.